Hello everyone, welcome to lecture week 5. So in this lecture, we're going to talk about a new type of model, which is called the decision tree. So let's look at what a decision tree is. So it is essentially a nonlinear model, right? So far we've been talking about linear models such as linear regression and logistic regression, but decision tree is a nonlinear model, meaning the decision boundaries are nonlinear, right? It's not a straight line, and the decision space is more complex, which means the decision tree is more powerful than typically a linear regression. All right, so let's look at how a decision tree is built. So imagine that you have some data sets, right? And say we have some columns, I have some rows. So this is our X, this is our Y, and we have some columns and rows. So this could be a classification setting where I have maybe ones and zeros. And this is just some input data. All right. So let's say I have 2 columns just to make the case more interesting. All right, so this is X1, X2, and we have 2 variables. So the process of decision tree is really to say what decision do I make to split the data so that's it's in the optimal way, right? So this is my original data sets, right? In this case, I have for example 4 rows, right? 4 rows. This is the original space of the data sets. Now the tree needs to grow, right? So it's, for example, it grows into the nodes, and maybe we have so the nodes will have a subspace, right? Subspace meaning maybe there's only 1 row here, and there are 3 rows, right? Could be 2 rows and 2 rows. So there are different decision points here. So the question is, what goes in here, right? So this is where we make decisions, and this decision concerns the growth of the tree, right? So I have 2 type of choices here. First choice is which variable do we choose, right? Which variable? So is it X1 or X2? All right, so that's the high level choice. And the second choice is which sort of threshold do we choose, right? So if, okay, so when I say threshold, meaning I'm treating the X1, X2 as a continuous variable, or if they're categorical, then I would say which category, right? Which category would I choose? So for example, X1 is categorical, it's a value between 1 and 10. Then I could choose value at 1.5, 2.3. So this could really go infinite, right? But usually our choice is in between the observed values. So I have, for example, 1, 2, 3, 4, right? My boundary is typically 1.5, 2.5, 3.5. And then I would choose among these 3 choices. Okay, so on the other hand, if X2 is categorical, meaning if it's yes, no, yes, no, right? So it can only take on 2 categories. Then the category is just is it Y or is it X, right? So say let's take X2 for example. So if X2 is equal to yes, and then the other side would be X2 equals to no, right? So this is a decision here, and basically this concerns these 2 choices. So we will first focus on the first choice. Oh, sorry. So the second choice. So this comes first in terms of our assessment. This represents how useful it is to use the current variable, right? And then second step is to compare across different variables and see which one do we use it here, right? So this is really a 2-level decisioning in terms of how which node and which specific threshold do we use in the current splitting. All right. So once we split, and it's like this, and we have 3 rows here, right? So this is still 3 rows. Now the reason why we take on the split because we hope that the resulting nodes, right? So the child nodes, which we call child nodes, the nodes are pure, right? Pure meaning that so if this is only one row, right, and it could be in this case the y is equal to 1, for example, right, and that's because there's no only one observation, which means if, right, if I have a new data point going here and my x2 is yes, right, x this, and it will always be predicted as y equals to 1. So y hat is always equal to 1, and it is correct because my true label is 1. So in this case, there's only one type of category in terms of the target variable in this node. However, these 3 rows, maybe there are 2 rows where x y equals to 1, but 1 row where x equal to 0. So there's some impurity here. So it's not so pure, it's impure, right? There's some impurity. And this is not what we want. So so we would like to further split the nodes so into further nodes, so that maybe there's only maybe this 2 y equals to 1 goes to here, and then the one row with y equals 0 goes to here, right? So we hope that by splitting this node, we can further improve the purity, right? So, or reduce the impurity. So that's the general direction I want to go into. And the reason is because once we have a pure node, then it is easy to make a prediction, right? We just need to follow the path, and then the prediction will be mostly correct, because this is only the pure node, meaning all the decisions will be exactly what the true labels are, right? So that's the general mechanism of growing a tree. And at some points, this is okay. So this is still the first stage. So we want to grow a tree, right? Grow a tree. And the second stage is really to prune the tree. So growing the tree is really the process of training or fitting the data, or fitting the model to the data, right? So it's again, it's built to minimize a certain cost function or loss function, right? So as you minimize the loss, you may see a very dense tree, right? So this is so if there's a dense tree, then the training error will go down very quickly, right? if it's dense, if it's complex. Now we also want, so what we want is really to say the test error goes down. But if it is a dense tree, then it means the model may overfit based on our last lecture. Then the training error may likely to go up. So a dense tree is not something we necessarily want, right? So once it's to be relatively regularized, so that is not so dense. So meaning this portion we can remove, right? If it's not really helping in terms of improving the model's generalization performance. So typically, when we prune the tree, then we have some loss function, right? And then plus some penalty, right? Now this penalty is on the complexity of the tree, right? Complexity. So this constitutes our cost, total cost. So we would, based on this cost, and then look at how to prune the tree so that those unnecessary branches that do not contribute to the overall improvements of the cost function will be removed. All right. So that's how we first grow the tree and then prune the tree. And then this process can go into the course validation stage as well. So there are multiple advantages for using a decision tree. For example, it can work for both regression and classification, right? So if in this case, the y itself is categorical, so it's regression, so it's classification. Now, if it's numeric, for example, 0.1, 0.2, 1.2, etc., then we can still use the same type of setup. But now our nodes, for example, here we will have maybe 3 rows. Now we have 3.2, 0.3, 0.4. Right? Typically, we would just use the average of all the observations in this node as the prediction, right? So this is our this is our decision rule for the regression case. So if that's the case, then we would hope that the observations in a single node would stay close to each other. Then we just use the average as the prediction. So it works for regression as well, right? And then we do not have any assumption on the distribution. So no assumption on the distribution. This comes a lot in simple models, for example, linear regression and logistic regression, because we require the data to follow specific distribution. For example, Gaussian distributed, or in the logistic regression, we assume the y, the target variable, follows a Bernoulli distribution, right? So in this case, we don't have any assumption on the distribution, and also it is robust, right? It is robust. This means that, for example, if my data is 1, 2, 3, right? So I can use that to be the linear regression. However, if my data changes to 1, 2, and 300, now this would change my regression estimates a lot, right? So the slope intercept will change a lot. However, in the decision tree case, it is more looking at the ordinal sequence, right? So 300 is still bigger than 2. So if I have decision rule to say if it's bigger than 2 or smaller than 2, then I make different decisions. And this outlier value does not really impact my decisioning too much, right? So if I were to use the middle as the decision rule, for example, this would be example 2.5. This could be so I plus and divide by 2, so 151. Now there's not too much impact because I'm still looking at just dividing the space by equally, right? So it's not as sensitive to the outliers, and it also works for the large data set as well. So in this case, if linear regression has a lot of data points, then the estimations could be very slow. But in this case, we're just looking at dividing the space into different subsets, right? So this we hope that they are as pure as possible or as homogeneous as possible, right? So in this case, it's more about decisioning, and the calculation is actually fast compared with other estimation procedures. All right. So let's look at a few terminology here in terms of when we have a decision tree. So we see this is a root node, right? This is a root node. This is where we start, and we call this is a splitting process. We split, right? And then we have some child nodes, right? Child node. And then when we have child nodes, this is also called parent node, right? Because it's a parent of the current node. And then this is also called leaf, right? So if we continue to go the tree, and if this is the end, this is the last layer, then this is called the terminal node. Node, right? So it's terminal, and this is terminal as well for this level, right? So this is called a branch, or it's called a subtree, right? It's a branch of the tree. So it's just different names we use to describe the tree and its constituents. All right. So the overall process of building a card, again, card represents the classification and the regression tree. So it's a tree that can be used to do both classification and the regression. So first, construct the training sets and build a tree in terms of what goes to our splitting decision, and how do we what combination would give us the minimum cost function, right? And then we look at prune the tree so that it's not overfitting. So this process likely will lead to overfitting, right? And we want it to overfit because we want to fit the data well first, right, in the first place. And now this is introducing a bit of regularization. So regularization by pruning the tree. So we bring it back a bit, right? Do not let it go too far away. And then this is ready to test the generalization performance. So it's generalization performance, right? So by assessing the model on the new data sets. So so let's look at the loss function itself. Typically, we use the surrogate loss function because the original loss function is difficult to optimize. For example, if you just use the accuracy, right? If we are doing classification and we would look at accuracy, but this accuracy is not easy to plug into the optimization procedure because it is combinatorial, right? So this is from the lens of the optimization perspective, if the problem is combinatorial, then it is difficult to solve. So cannot compute the derivative easily. But in this case, it's a sim challenge. So that's how we switch to the surrogate loss function so that this one approximates the accuracy, right? Approximates, but then it's not exactly the same. So it's safe. So as we minimize the surrogate loss function, we hopefully accuracy also improves, right? So improves, right? So this is something I want to lay out. And then we have two different choices here. So if it's categorical outputs and if it's continuous outputs. So typically for the categorical outputs, in terms of the loss metric we use, we can use Gini impurity measure, right? Impurity measure or impurity index. So that's one to do. And we can also use entropy. So talk about these two definition later. And then if it's continuous outputs, then the loss metric can be the sum of square errors. This is same as the linear regression, right? We can also look at the absolute error. So absolute error, which is less well widely used, but still can be used, right? So the absolute error of the classification of the regression. All right, so so the best splitting point for each input is really we would again we would hope that the nodes would go from impure to pure, right? So the tree setup, and the way we do this is we measure the level of impurity, right? So this is this again comes down to the reduction in impurity, right? So impurity, and we will look at the split point that gives us the maximum reduction in impurity. So that's what we want to do when we look at splitting the tree. So the Gini impurity measure is defined as so it's correct as the I stands for the impurity index, right? For a specific node. So why is a node? Because a node is a state we're looking at, right? So it's for example, it's a node, and we have its classification, right? So for example, we have this represents the ones, and this represents the zeros. So we have 3 observations where y equals to 1, 2 observations where y equals 0, right? So this is set up. So the calculation is goes by this. So we can this defines 1 minus the sum of the sum of the squares, right? Of the probability squared, right? So for example, the C represents a category. The category can go from 1 to the total category K, right? So let's look at let's plug this in and then do the calculation. So in this case, it would be 1 minus we do summation here, and what if C equals to 1, right? Then we have then the probability of y equals to 1 in this case is 0.6, right? Probability of y equals 0 is 0.4. So we just take each probability, square it, and then add them up, right? So this is how we do the calculation. So that's the Gini index for calculation for a specific node, right? So that's for one node. Now we're going to split these nodes into different sub-nodes or child nodes, right? So we have maybe 1, 2, and then we have then we have 2 remaining here and 1 remaining here. So the reason why we have this splitting result is because we use some decision here, right? So this is the decision on which splitting point we use. Now this splitting point gives us this specific result, and we can calculate the, for example, this is B, this is C, this is A, right? We can calculate the impurity for the node B and impurity for node C, right? So this is something we can calculate. And then next would be aggregate this individual impurities, so have over impurity. So this aggregation is really to look at how many observations we have. So in this case, we have 2 observations, right? So it's 2 over total of 5 observations. This is 3, so we have 3 over total of 5. So this is the proportion of the samples in this node, right? So now this the overall Gini impurity, right? The impurity for the combined nodes is 2 over 5. This is a proportion, then multiplied by the impurity for node B. So this is essentially a weighted sum, right? Which is summing, weighting the impurity indexes and then summing together. So this is what we have. And now this is another result that represents the impurity for the overall child nodes. Now, if we were to take the difference of these two, right? So we use IA to minus this one. So this represents our reduction, right? Reduction in the impurity, or in this case, in the Gini index, right? So reduction in Gini index, and we want to maximize it, right? We want to maximize it. So when you look at the decision here and here as well, right? So in terms of which variable we use and which specific splitting decision we use here, we want to maximize the reduction in the Gini index. So which means this is a tedious process, right? We need to look at different potential decisions, and then find the one that maximizes, gives us the maximum benefit in terms of reducing the uncertainty in the Gini index. All right. So the entropy and information gain is really another measure. So if you look at the entropy, then the entropy is defined as this. We will still take the proportion of a specific category, and then take the log, the base 2 log of the proportion as well, and then we add them together, right? So this is for all the categories, and then take the minus, just make the measure positive, right? So this is another way to measure the impurity, and this is also quite widely used. So now information gain is really looking at how much of reduction in the entropy. So in the previous case, we have the entropy for A, and we have entropy for B and C as well, right? B and C as well. And then we get the proportion. This is 2 over 5, 3 over 5, right? And then plus together. So this is the entropy for the next layer. Then we look at the improvement or reduction in entropy. So this is called information gain. So how much of information we have after introducing a specific splitting decision, right? So this is called the information gain. The case for regression is more intuitive. So say we have so the sum square is really defined as for a specific. So we have different points here, and for specific nodes, then we have the average, and then so this is average we have as our prediction. So our prediction is average. Now the sum square error is defined just as the HY, right? HY minus the the prediction y hat, and then square, then which adds all the instances over I, right? So this is some square. So if we have some decision for splitting the nodes, then we have something else. So this is similarly can be done. So we can calculate SSE for this one, SSE for this one, and then do a weighted sum of the weights, and then we get a sum. So they have another SSE, and then we look at how much of a reduction in the sum of square errors we have after introducing a specific splitting decision. All right. So pruning the tree is really similar in terms of how we regularize the model. So we have some so previous look at the cost function, the loss function, or this really represents the improvements or reduction in impurity, right? Or it can be a misclassification rate, right? So in terms of the final performance measure, and then we would build on this loss function and then build in a sort of penalty. So this could be the number of leaf nodes, right? Leaf nodes. So meaning if a tree is very complex, then we have a lot of leaf nodes. So this is leaf nodes. Then there's going to be a penalty here, right? So we multiply it by alpha as our trade-off parameter. So this gives our overall cost function, and this is the cost function that we want to minimize by validating against the validation set, right? And then prune the tree. So that's the overall process here. And pruning the tree is really means, for example, we will look at a subtree, right, a branch. So is this necessary, right? If it's not, then we will remove it, and then of course we remove that, we choose another one to connect to it. Right? So this one supposedly approximates the original decision point here, right? So before we finish up, just to add a bit of extensions, random forest. Random forest is takes the decision tree to a step further. So we have if we have one tree, then this should really have multiple trees. So each tree is a bit different, right? Each tree is a bit different. So for example, this is this one, and then this is one decision tree, two decision tree, three decision tree. So this all comes from the original data set, right? Original data sets, and then we build three trees. So this is called bootstrap approach, right? Bootstrap. So meaning we actually create multiple versions of the original data sets, and then this is called bootstrap because we create artificial data sets, right? By randomly sampling from the original data set in terms of rows, and then also randomly choose the columns we use, the features we use. So each tree is different, and it is expected to be independent and uncorrelated to each other, right? You just like a different set of skills, and then look at the problem from different angles. Now we have different predictions here, right? So this is y hat 1, y hat 2, y hat 3. Then we would average, right? Take the average. So sum, then average. So this is called aggregation. So we aggregation. So we aggregate all the individual models together, the submodels, and then aggregate together. So this is called the bagging. So essentially, Bootstrap uses bagging to make a final decision. So this is our final prediction we had, right? But the individual piece is the same in terms of how we build a Grover tree. So the process is quite computationally intensive. All right, so that's it for this video, and thanks for watching. Hope to see you in the next video.